Good morning. So the last session, we have started the definition of a sequence, and then we have also talked about when we will say it is convergent and converges to certain limit. Now, and also we have seen the algebra of sequence. Means like how would you perform the sum of two sequences, product of two sequences, or quotient of two sequences. So if you look at inside the sequence, it's nothing but a function, okay, which is defined on set of natural number, and we are talking about a real valued sequence. So we are talking about a function set from x from natural number to r. If you're talking about real sequence, means whose range is a subset of r. So if you talk about complex sequence of complex numbers, so the range will change here. So it's going to be c2, okay, this r2, okay, and so on. So you can that will be generalized maybe when you talk about the sequences in function of several variables. But then we have looked out when you identify that's a sequence of real numbers, then you are certainly trying to know where does it converge, okay, or in other words, for large values of n, where it will be closer to certain point, okay, so or it is going to be in the neighborhood of a certain point. That's what it means, okay. So this is what we have seen. What are the definitions? Now we are going to look at some of the properties of it. So if you, the first result is if x is a convergent sequence of real numbers, and if xn is greater than equals to 0, means it's a sequence of all non-negative real numbers, okay, which can never be negative, is always greater than equal to, you take any member, it will be always non-negative. So what is the intuition is its limit also going to be non-negative. So if I claim this result, it has a very simple proof. It's very simple proof. If I claim this, suppose this is true. Okay, so these two results will certainly follow by looking at this result. Okay, so suppose this, for this you can say theorem 1, this is theorem 2, this is theorem 3. Okay, so if theorem 1 holds true, then we can show that theorem 2 and theorem 3 are nothing but the corollary of them. By just you just have the x and y are convergent sequences of, suppose I just look at theorem 2, what it says is if x and y you are taking two sequences, okay, and they are such that you take nth terms, any nth term, okay, then xn is less than equals to yn for all n in natural number. Okay, so when you take nth term, you can make a comparison between them. Then their limit also follows the same rule. Okay, so what you can do here to utilize the theorem 1, you can define sequence z by x minus y. If I define the sequence, or y minus x, okay, y I have chosen y minus x, you will certainly come to know in a few minutes. So y minus x, you know, how will be identified as yn minus xn. Now since this holds true, okay, so xn is less than equals to yn, so nth term of this sequence always positive, so yn minus xn is strictly greater or is going to be greater than equals to 0. This is sequence which has the property that its nth term is always greater than equal to 0 for any n. That's the first thing. Second thing is, here it is pre-assumed that both the sequences are convergent, x and y are convergent, so their sum and difference will also converge, right? So therefore this z sequence is also converges. Okay, so z is a sequence of real numbers such that its nth term is greater than equals to 0 for all n in n. So then theorem 1 tells you that their limit, the limit of this is greater than equals to 0. So when you take about limit, so you can, so since, so limit of y minus x is what? So if you talk about the limit of Zn, so nth element is nothing but the limit of yn minus limit of xn. From the previous result that has been shown. So this certainly is greater than equals to 0 because of the theorem 1. So which establishes the result that limit xn is going to be less than equals to limit yn. So this is called one of the comparison tests, you can say. Okay, so this is one of the comparison tests which you can use to claim that certain sequence is dominated by another sequence, and the another sequence is you can talk about, suppose this converges to this converges or this converges. So you can talk about certain properties. Okay, that we will look at. Okay, comparison test. Okay, now how will you go for this theorem 3? So I think this is very clear now. Now how is theorem 3 will go? So x is a convergent sequence and its terms, so convergent sequence, you know, anyhow every convergent sequence is bounded, means mod xn is less than equals to n for all n in n. So suppose you have a is this xn is lies in the closed interval a to b, then intuition says that also lies inside this interval a to b. But how do you claim it mathematically? So for mathematically, what you will do is you can identify this sequence a. You can you can define a sequence y whose nth term is a, means constant sequence, and which is convergent. Okay, so constant sequence that can be shown that this is convergent. Similarly, you can identify this b by z where nth term is b. It's again a constant sequence which also converges. Now for this yn is less than equals to xn. So its limit, also use theorem 2, limit of yn is less than equals to limit of xn. Now take the second inequality here, xn less than equals to zn. Okay, so then limit of xn is going to be less than equals to limit of zn. But limit of zn is b, limit of yn is a. So if you combine both of them, this will immediately implies that a is less than equals to limit xn less than equals to b. Okay, so from these results, what you observed is that if you are able to identify two sequences by this, so you can talk about something about it. So okay, so both are, so note that both are assumed to be convergent sequences. Okay, that okay. Now fine. Okay, so now let's establish the result of one. This is also a 1 or 2 line proof. It's not a big proof here. So I just want to introduce this. Okay, so if I look at the proof of theorem 1, so it says that you have the sequence x where each term is non-negative for all n. Then your claim and x convergent converges. Okay, right, because there are sequences which are non-negative but not converge. You can talk about the sequence of, means like natural numbers 1 2 3 4 5 6 7 8. Okay, this sequence also satisfies this property. Okay, so let limit of x, or means like limit of xn is say x. What is your claim is this limit certainly is greater than equals to 0. That you need to prove. So these are the things given to you and this is your claim. Okay. Now, how would you claim? So you are going to use the contradiction. So let x is less than 0. So you can't use equal to here. Okay, because we want to show that greater than equal to 0. So on the contrary, you just start with x less than 0. So what will happen? Okay. Now what you do is, so x is less than 0. Is there any real number? So minus x is positive. So you can define epsilon is equals to minus x, which is greater than 0. Now, note that the definition applies here now. For every epsilon bigger than 0, you are able to find a space afterwards. All the terms lies inside the neighborhood of x by neighborhood of x with the you can say with the radius epsilon. Okay, so define epsilon greater than 0, and since limit of xn is x, so there exists a k which is certainly depending on epsilon in n such that mod of xn minus x is going to be less than epsilon for all n greater than equals to k. Okay, right. So now what you can do is, now you just use the equivalent definition of modulus function. So means this is implies, if you open it up, so minus epsilon less than xn minus x less than epsilon for all n greater than equals to k epsilon. This implies, so now you take x here, so x minus epsilon is less than xn less than x plus epsilon for all n greater than equals to k epsilon. Now I want you to point out where the problem is happening now. Is there any problem here? So does it contradict to anything?
Sir, x plus epsilon naught is greater than 0.
X plus epsilon?
Greater than 0.
No, see, epsilon is minus x. So what if you take x plus epsilon, what it will be? 0. You are defining epsilon equals to minus x, which is going to be greater than 0.
Sir,
Okay.
X is less than 0.
xn will be
less than
negative.
0 here.
Pardon?
Xn would be less than 0 here.
Yes, and it contradicts.
So yes. So this is means like this is equals to 0. X plus epsilon is nothing because epsilon is minus x. So x plus epsilon is 0. So what it contradicts to? So this is going to be contradiction to the fact that xn is greater than equals to 0 for all. But you have found the space afterwards means that xn is strictly less than 0, which cannot happen because you have been given that xn greater than equal to. But this is happened because of your assumption that let x less than 0. So this cannot be possible. So this tells you that your claim is true, hold true, that x is greater than equal to 0.
Sir, I have a question here that modulus of xn minus x, we have just assumed that it is less than or epsilon naught. Everywhere we are taking less than equal to epsilon naught. So intentionally we have not put it here equality. So we are contradicting so, or it would be less than.
No, in the definition you have a strictly less than epsilon, not less than equal to. So why it is important is because epsilon is if the epsilon is strictly greater than 0 number. If you take greater than equal to 0, then here equal to can be taken. Why? Because we want infinitely many terms should be sitting very close to x or on the x itself. You can say means like after, see, when you in other words, suppose you are looking at the solution of some equation, okay, but you cannot solve it analytically, suppose. So what you will do, you are going to generate a sequence of approximation. Okay, so if you are generating the sequence of approximation, suppose, so the numbers will be generated, let's say y1, y2, y3, and so on. Where do you will stop? You will stop whenever the yk and yk plus 1 are very close. Means rounding off means like up to 4 decimal place or 5 decimal place or 8 decimal place. So it's going to be on the number when it means like afterwards it's very close to 4 decimal place. So that is what here limiting means. You can also look at it. Okay, so we want the infinitely many terms to be sitting on X also in the limiting sense. Okay, because this is see, 0 less than equals to this. So this can be happen for every n greater than equals to k epsilon for a given epsilon. So afterwards, what is telling? See, xn is going to be sitting on X infinitely many members, means very close to X. Okay, because since if it is true for every n, then it is xn is X only, constant sequence. Right?
Okay, sir. Yes.
I think this example will make clear here that if you look at the approximation of the solution, definitely you want to stop at some place. Where do you stop? So either this sequence of approximation will converge or diverge. Means it may take you away from the solution as well. So how do you look at it? So you will definitely look at some test equation and look at the problem and try to evaluate the error things. And if error are monotonically increasing, you can say, so means it's diverging from the solution. It's like it is not going towards the solution. Okay, so but what your expectation is, it should move towards the solution only, which is the desired solution. So what will be the desired solution? The limiting value, but which cannot be achieved. So limiting value will going to be an exact solution, but your limiting so xn is going to be an approximate solution. So after some large value of n, it should be very close, like you are getting suppose 1.4142, and the next number you're getting 1.4142, 1.4142, let's say 50, and so on. But these numbers are very close to 1.4142. So afterwards also you will get the pattern that it is going to be exact till 4 decimal place. So it is going to be you can say that this is a better approximation, this is a good approximation to the solution, and you can just stop your means like programming or other things. Okay, right? So you can make the stopping criteria. So their epsilon will be treated as a, you can say, as an error tolerance. You can give epsilon equals to 10 to the power minus 6. Where do I stop? Okay, so these things can be used. Epsilon is mathematically, it looks very tedious job, but it's going to be in coding when you're going to use this, are going to be used like a error tolerance. Okay, and you have to see how would you able to minimize the error terms. Okay, right. So this establish the result that limit of the sequence of positive real numbers is again going to be positive. Okay, right. Okay, so this is the next result. It's also a very immediate result from the previous result. So which is also known as squeeze theorem, or also known as sandwich theorem. Okay, why it is called sandwich is because you have three sequences. Xn converges to let's say xn converges and zn converges. So where does this yn goes? Yn also should converge, and it where should it converge? Is it converges to the same limit if limit xn is equals to limit zn. Okay, so this is what the sandwich theorem says. So it will help you to establish the result, which cannot be proved like immediately or something. Okay, so that we are going to look at. Okay, so here let's say these x, y, and z are sequences are such that so xn is less than equals to yn less than equals to zn for every n in n. And suppose the limiting value of xn and limit zn means then x and z are convergent sequence. So if you are okay, so we are going to talk about more. Okay, that let's say suppose xn and zn are such that they are converges and both converges to the same limit. Okay, then the middle sequence also convergent, and it converges to the same limit where the xn and zn goes. Okay, so for example, so just I will start with an example, and the proving the result is very simple. Okay, so let's say you are talking about the sequence y is equals to sine n by n. Okay, so either you start with sine n, you know where does it lie. So sine value for any value of x, it lies between -1 to 1. So it's a bounded. So numerator is bounded. Okay, so the denominator will dominate it. So when it is, so limiting value is going to be 0. Okay, that can be get by intuition. But how do you establish this? I know that I will use the fact that -1 less than equals to sine n less than equals to 1. I know for every n. So what I will do, so n is a natural number, so it's a positive. So I will just divide both sides, or multiply by n. And now this can be treated as your xn, this can be treated as zn. Both limit goes to 0. So this result can be used to state that limit of sine n by n also tends to 0. So only need to show that now limit of zn is 0. Okay, so instead of sine n, suppose cos n is there, so that example also you can take. Okay, so sine n, you know, you have used the fact that sine n is bounded between between -1 to 1. Okay, then you multiply by, so you have to find the comparison here again. The xn is less than equals to yn less than equals to zn. Now look at here, so xn is tending to 0 and zn is also tending to 0. So certainly the in between the which is sequence is sitting here, that also should tends to 0, right? And that is guaranteed by this sandwich theorem. So you can certainly write by sandwich theorem that 1 by n is equals to limit of, so since limit of zn is equals to limit of xn, so limit of yn also does converge, and the limit of yn is the same as this. So you need to only find out the limit of this. So what is the limit is, that is very simple to prove, 1 by n. Okay, limit of zn is 0. And use the, and refer the result that you are using the sandwich theorem. Okay, right. So like we have also done one problem which is if you recall from the previous, that another example is I'm just bringing from the previous example, square root of n plus 1 minus square root of n is equals to 0. And we have rationalized this, and then we have found that let's say this is yn is equals to square root of n plus 1 minus square root of n. Now you multiply and divide by square root of n plus 1 plus root n. Okay, then it will be, you know, 1 by square root of n plus 1 plus square root of n. Now you can note that this, you know, square root of n plus 1 plus root n. So you know that square root of n plus 1 plus root n is greater than equals to 2 root n and less than equals to 2 square root of n plus 1 for every n. So you have found that 1 by 2 root n plus 1 is going to be less than equals to 1 upon square root of n plus 1 plus root n, and less than equals to 1 by 2 root n. Now you can call this sequence is xn, this sequence is yn, this sequence is zn. So these results are only useful, this result is only useful when you are sure that left this left side the sequence xn, and right side the sequence sitting on the yn, okay, so side of yn. So both are convergent and converges to the same limit. If you are assured about it, then you can use that result. Otherwise, there is no point to consider such inequality. Okay, so it can be shown that limit of xn is equals to limit of zn that was equals to 0. That I have already shown that. For this, similarly, you have to follow the similar way. Okay, right, and then this implies limit of yn also equals to 0. Okay, so this also is using the sandwich theorem. Okay, now if you take another example, right, you have the sequence is let's say 1 by n square plus 1. Okay, so you know that this is 0 is less than 1 by n square plus 1, less than 1 by n square. Right, now you can show that this tends to 0. This sequence is constant, and constant sequence also tends to 0. So the squeeze theorem tells you that this also tends to 0. Okay, so you can use the result. So similarly, instead of now 1 by n square plus 1, you can consider the example, right, like x equals to sine n by some another n square plus 1 also you can use. Okay, now use the fact that sine n lies between -1 to 1, then it is certainly -1 by n square plus 1 less than sine n by n square plus 1 less than 1 by n square plus 1. Now you can show that 1 by n square plus 1 tends to 0 by using this, and then use the sandwich theorem here to imply that this limit is also exists and it is equals to 0. So here, see, look at here. So what we are using the sandwich theorem, okay, but we are doing the part that here that you have to show that limit 1 by n square is 0. So that you need to show, okay, when you are talking about mathematical. Okay, means for a given epsilon bigger than 0, you have to show that limit of 1 by n is going to be 0. 1 by n square is going to be 0. Right. Okay. Now let's talk about some more results. So absolute sequence, like absolute thing. Okay, means when you have a convergent sequence. Okay, suppose x is converging. Okay, let's say x is sequence xn, which is converges, and some we are also denoting that convergence is x is converge to x. Let's assume that. So then what will happen to, if you look at the modulus of the each sequence, whether does it converge to the mod x? That result also hold true. So by looking at this result, then the sequence mod xn of absolute values converges to mod x. That is if this happens. So this is this is going to use the fact that so mod a minus mod b, if you prefer this inequality less than equals to mod a minus b. Okay, so once you know or aware about this result, replace a by xn and b by x. Okay, and then use for every epsilon which is working for xn to xn, which also work for xn. Okay, so that detail I'm not going to give, but what is important here, if the sequence converges, then it's absolute. If you replace xn by absolute values, okay, that also converges to mod x. Okay, means converges to the absolute value. So why it is, because is modulus function, if you are going to look at the property of modulus function, it is continuous. So, and then later on when you talk about function of single variables, so when a function is continuous, it preserves the convergence. Means whenever xn converges to x, then its f of xn also converges to f of x. And this is in fact in some textbook it is also a one of the definition that if this xn converges to x implies f of xn converges to f of x. Then you have the function continuity, and continuity implies the same. So these are if and only things. So that we will talk later on. Okay, but modulus function is continuous function that can be established, that we will establish in during the class session for function of single variable. Okay, so but what will about the converse? So converse may or may not hold true. Okay, that we will look at in the session for infinite series. So next result is very useful for you can say infinite series, but here also it also going to be useful in some sense. So you have this result. So we are going to utilize this result. So let's just try to understand how do you use it and what it is telling you. So let xn be a sequence of positive real numbers. So xn, so you have given sequence. First, you have to identify that it is a sequence of positive real numbers. Means every member is greater than or equals to 0. And suppose that limit of xn plus 1 by xn means the ratio of future value and present value. If you take the limit, then it should exist. You don't know about what about xn, limit xn. Okay, but suppose you know xn is less than or equals to xn plus 1. Suppose you are able to identify any relation between them, means that they are decreasing sequence or increasing sequence. We are going to talk about in a few minutes that one will say a sequence is decreasing or increasing. Okay, so suppose you take the ratio of the future value and present value, and if the limit in the limiting sense it does exist, and further if this limit is strictly less than 1, then it gives you guarantee that xn converges and limit of xn is 0. Okay, so let's use this result and to establish some of the convergence of certain problems. Okay, right. So which is also certainly part of your the assignment as well. Okay, right. So let's look at some of the example now. So we have the first example is let's take the exercise from your reference book. So let's take the first example here. So you can refer the problem number 16 in section number 3.2. Okay, so we have this is let's say a to the power n, and you have seen that this let's say 0 less than a less than 1. You have already seen that this sequence converges to 0. Okay, so let's verify with the previous result. So whenever you are establishing certain result, you must verify it with some very simple cases. Okay, so that's always a good thing to see that whether your method is working or not. Okay, so here in the sequence, let's say xn plus 1 is divided by xn. If you take the ratio, what it will be a to the power n plus 1 by a to the power n, which is going to be a. So xn plus 1 by xn. So if you take the ratios, these are nothing but the constant. Constant is a. So this sequence certainly converges, and this implies limit of xn plus 1 by xn. You know that the constant sequence converges, and this certainly is equals to a. Now you can decide about the two cases. So a is greater than or equals to 1. You can't decide use of previous result. Okay, that result is only help you whenever the right hand limit is less than 1. Okay, then only this result is applicable. For L greater than or equals to 1, you can't judge. Okay, right now there is no other way to. So let's say a is less than 1. So this implies the previous result gives you guarantee that xn converges and limit of xn is 0. Okay, since you have given that a is less than 1. Now see, if I go back and ask you whether L is greater than or equals to 0 always.
Yes, because it is sequence of positive real number.
Yes, so ratio is also remain positive. It's a limit of the positive sequence. Okay, so limit is always a non-negative. So that's true. Always get equal to 0. Okay, right. So fine. So this is very much required that a is greater than 0 here. Okay, right. Now let's take the second example. One example is another example. Let me take is n by b to the power n, where it is given that b is greater than 1. So we are going to take the help of the previous result. So certainly we are going to compare the ratio of the future value and present value. So that is going to be n plus 1, xn plus 1 divided by b to the power n plus 1 divided by n by b to the power n. So what it will be, n plus 1 by n time 1 by b, right? Yes. Now, so this can be written as 1 plus 1 by n time 1 by b. Now you use the algebra of limits. Okay, so this is your limit of constant sequence. So you know x plus y. If x converges, y converges, the limit of x plus y converges to the sum of the limits. So you can take 1 as a constant sequence, 1 by n is another constant sequence. Then apply the scalar multiple of sequence also. You can do that. So certainly this limit, so you are going to refer those results and you can certainly show that this is going to be 1 by b. Okay, as n tends to infinity. So this gives you limit of xn plus 1 by xn is equals to 1 by b. Since b is greater than 1, certainly less than 1. So b is non-negative, right? B is greater than 1, so b is greater than 0. So 1 by b is also greater than 0. Okay, and you can verify that xn plus 1 and xn is a positive sequence, is a sequence of positive real numbers. So the previous result shows that limit of xn is equals to 0 since L is less than 1. Okay, so with this example we will close this result now. Okay, right. So you can work with another results like n factorial divided by b to the power n and so on. So are certain other results which you cannot directly handle. Okay, but you can handle with this result. Okay, right.
Sir,
Now,
I cannot understand last step. Limit xn is equals to 0.
yeah, this is due to the result which we have learned. Okay, this is due to the you can say theorem what we have called 1, 2, 3, right? So previous results 1, 2, 3. So let's say this is 4 and this is 5. So due to the theorem 3, or 5, sorry, 5. So which says that if limit of xn plus 1 is equals to L, it is this limit of xn plus 1 by xn is L exists, and if L is less than 1, then it gives you guarantee that xn converges and its limit is 0. Let me give you the proof. Not okay. Okay, so let me establish the theorem. Okay, so you can so proof of theorem 5, you can say. Okay, so what is given is xn is a sequence of positive real numbers for every n. What another thing given is limit of xn plus 1 by xn is equals to L. L is less than 1, but we certainly observed that is greater than equals to 0. Okay, then our claim is limit of xn is 0. It exists and this is going to be 0. Now, so if proof is as follows, so So L is less than 1 is greater than equals to 0. So let 0 less than R less than 1 be such that L less than R less than 1. So why we have chosen an R which is strictly greater than L means strictly greater than 0. Okay, so this is one of the important thing here, because if R is 0, if L is 0, we can't say anything right now. Okay, right. So let L is less than R. So this certainly will identify. So L is less than R. So we can define epsilon is equals to R minus L. It is strictly greater than 0. Right. Now, since limit of this exists, limit of xn plus 1 by xn is equals to L does exist. Okay. So therefore, there exists a k epsilon in N such that what happens is mod of xn plus 1 by xn minus L is less than epsilon for all n greater than equals to k epsilon. Right. Now open up the definition of this modulus. So this implies mod of open up this. This is going to be minus epsilon. So you minus epsilon less than xn plus 1 by xn minus L less than epsilon for all n greater than equals to k epsilon. Now take L on means some L. Okay, so L minus epsilon. You both all the in the all the inequality. So you take L on. So this also remains true. Okay, this implies L minus epsilon is less than xn plus 1 by xn less than L plus epsilon. But epsilon is R minus L. So L plus epsilon is R for all n greater than equals to k epsilon. So what this tells you that xn plus 1 is less than R times xn. Since xn is a non-negative. Okay, xn is a non-negative greater than equals to 0. So you can certainly move this xn on this side for every n greater than equals to k epsilon. So use this is less than R square times xn minus 1. Right? And so on. This relation is hold only for n greater than equals to k epsilon. So this is going to be less than x to the x k epsilon R to the power n minus k epsilon plus 1. Okay, so if you sum up, so n plus 1, this is there, n plus 1. So 2 plus n minus 1 is n plus 1. So this also sum is n plus 1. Now, what it will help you? So this is going to be, this is nothing but you have, this is x k epsilon time R to the power 1 minus k epsilon time R to the power n. Right. So this is some constant which you can denote it by something, right? This is equals to some c time Rn. Now since R is positive, xk epsilon is positive, this is always a remaining positive constant. So what you obtain is xn plus 1 is less than c time Rn, and you know that 0 less than equals to Rn plus 0 is less than equals to xn plus 1, which is strictly less than c time R to the power n. And now note that 0 less than R less than 1. Now use the fact that this tends to 0 as n tends to infinity. This is a constant sequence tends to 0 as n tends to infinity. So the Sandwich theorem gives you guarantee that this also tends to 0 as n tends to infinity. So this gives you guarantee because use of Sandwich theorem here. Okay, so C is always a positive constant. There's not a doubt about it. And R to the power n tends to 0. Why? Because 0 less than R less than 1. We have already shown this, that this result tends, this sequence tends to 0. So this claims that the action converges, and where does it converge? It converges to 0. Okay, so I hope this is clear now.
Sir,
Yeah.
please repeat our second last step. Xk r raised to n minus k plus 1.
Okay, this one.
Yeah, yes.
Okay, okay. See, we are using the recurrence relation now. So to make it dominate further. Okay, so to dominate further is you have to find out the pattern. What should be the last term? Since this result is hold true for n greater than equals to k epsilon, so you can't go below k epsilon. It's like k epsilon minus 1, k epsilon minus 2, and so on. They further the inequality may or may not hold true. Okay, so what happen is here is, so this implies this is you can add with this term. So how will you identify the pattern is by looking at the suffix of x and looking at the power of r. So r suffix and power sum up is n plus 1 in each term you can look at. So when you are ending with xk epsilon, because you can't go beyond xk epsilon, so you have to add with xk epsilon. So what should be the r power? It should be in such a fashion that sum of the power and sum of the with the suffix of x is going to be r plus 1. So what should be, so k epsilon plus 1 is plus k epsilon is k epsilon get cancelled n plus 1. So you are following the actual pattern. Okay, and then we have just extract r to the power n from here, and rest of the things I have put down in the constant because it's remain fixed, it does not change. Okay, and r is also a fixed number. Any number 0 less than r, l 0 less than r less than 1, and such that l is strictly less than r. Okay, so this is a fixed number, only varying is n. So now it's look like the sequence is a to the power n. Okay, and which you know that converts to 0 as n tends to infinity whenever 0 less than a less than 1. Okay, so this I hope this is how we have got this last point. I think that is clear now.
We have so that limit x n plus 1 is equals to 0, but we prove that n is equal to 0.
So what you can do is you replace n by n minus 1 in the above. Okay, whatever we are following, so you just replace n by n minus 1 everywhere, so you will get the result for xn. So see when limit xn is equals to 0, limit xn plus 1 equals to 0. For a large value of n, it doesn't matter. Okay, so whether n plus 1 or n plus 2 or n plus 3 or n plus k, it doesn't matter. Okay, so you can replace everything by n minus 1 if you are very strict with the finding the limit in terms of xn. That's not it. Okay.
Okay.
Okay, so let's define the definition for monotone sequence. So I hope the behavior, it will be clear that let x be a sequence of real numbers. We say that x is increasing if it satisfies the inequality. So x1 is x is increasing means like here they are they have been put in down in the some order. Okay, so what is the order is we are starting with the lowest value. Certainly, so increasing means it's starting with some lowest value. That's sure, but we don't know what will be the upper value, upper bound. Okay, so if it satisfies the inequality x1 less than equals to x2 less than equals to x3 and so on. Okay, so since sequence is enumerated here, so sequence is always a countable. Okay, sequence, these are countable because set of natural number is countable. Okay, so because you can identify a bijection from n onto n for the sequence. So you have this x1 less than equals to x2 less than equals to x3 and so on. If you have this behavior for the sequence, okay, then you will say that this is an increasing sequence. Okay, now we say that x is decreasing if it is a reverse way. So means you have started with the largest value, then it is going smaller and smaller and smaller and so on when you go for the large value of it. So for example, if I look at the example like 1 by n. sequence 1 by n. So you know that this is going to be, you know that you can't decide what is the lowest value, but it's strictly less than 1 by n is, you know, right? So it's a decreasing sequence. So 1 greater than equals to 1 by 2 greater than equals or strictly greater than here, right? Greater than 1 by 3. Okay, greater than 3, greater than 1 by 4, greater than, and so on. And that is going to closer to 0. Okay. So we say that x is monotone if it is either increasing or decreasing. So for the increasing case, you can consider the sequence n, sequence of natural numbers. So that is 1 less than equals to, or we can say 1 strictly less than 2, less than 3, less than 4, less than 5, and so on. This is the increasing sequence. Strictly increasing, you will say. This is strictly increasing what we have. Okay. So now the question comes whether it always converges. So if you look at the behavior of increasing sequence, it's going to be x1 less than equal to x2 less than equal. So you are increasing with the xn. Okay, so where does it converge? If it converge to the least upper bound. If you look at here, okay, where should it converge? It should converge to the supremum of this. We can say set xn. Okay, so because for large value of n, it is not coming towards x1, so you can't say that x1 is the limit. It is it's going away from x1 towards, like, either to infinity, either to the infinity side, plus infinity means like divergent, or it is going to converge to the supremum of this. Okay, that we are going to show. Okay, so but when it happens, that we also make that. Similarly, if you look at the behavior of the decreasing sequence, it will not definitely it will not converge to the largest value. It's going to, because whenever you are going with increasing your n, you are going towards the minus infinity, you can say. Okay, so if it is going to diverge, it's going to diverge towards, I can say, sometime minus infinity, or if it is not, it's not convergent. Or if it is convergent, it's going towards the lower bound, or in other words, greatest lower bound, which we have denoted by infimum of the set. So when this lower bound exists, when this infimum exists, when the set has a lower bound, means, so it is already have an upper bound, so it has also it also have lower bounding, means sequence is bounded. So this gives you the intuition that the monotone sequence converges if and only if the sequence is bounded. So once any of the sequence is bounded, so this sequence is bounded above and this sequence is bounded below, then this certainly converges. Okay, so this is the result which we are going to see now. Okay, so you have already seen if the sequence is convergent, then it is bounded, but it is like inverse. Okay, so if a sequence is monotone, is either increasing or decreasing, okay, and bounded, okay, then it is convergent. But you have noted that every bounded sequence does not converge. Okay, so that also we have seen. Okay, so we have the result that a monotone sequence of real numbers is convergent if and only if it is bounded. So if you are to only see that whether the sequence is convergent or not, you need to see whether the sequence is bounded, it has a monotone behavior. Okay, if you are interested in the limit, then you can go further. Okay, so for example, you have the sequence 0 less than 1 by n less than 1. This is a bounded sequence. Similarly, 0 less than 1 by n square plus 1 less than 1. Right? So these sequences are having monotone behavior. This is decreasing sequences, but they are bounded, so it does converge directly. So if you want to answer this converge, yeah, this because of its the monotonicity and boundedness of the result. But where, if suppose somebody is asking you that where does it converge, So what will be the limit? So if xn is a bounded increasing sequence, then it's converges to its least upper bound. And if x is a bounded decreasing sequence, then its limit is greatest lower bound. Okay, that can be shown very. It's also a tricky proof. It's very tricky proof. So let's do with it. Okay, so I'm going to use I'm going to do for the first result. Okay, and just give you the idea. Okay, so let's call this as okay. So let's call this as theorem number 6. Okay, right. So what we were trying to establish is let x equals to xn is increasing and bounded. So your claim is convergent and converges to the limit is going to be supremum. Okay, right. So now since it is bounded, so this implies, so since x is bounded, means there exists capital M in real number such that xn is less than equals to m for all n belongs to natural. I have not used mod xn. Okay, I have not used mod xn. Okay, but this still remains true. Mod xn is strictly less than equals to m, so xn is less than equals to m. Okay, so this remains hold true for all n in belongs to natural number. Now, see, this is a set. Sequence also is a set which is countable set. Okay, which is non-empty and it has an upper bound. Okay, so every member is less than equals to some you have one real number. Okay, where it is means every member is bounded by lies below of n. So what does it mean? Completeness property of R gives you what? Gives that X has supremum. Let's say this your X is equals to supremum of this set Xn such that n belongs to natural number. Now our claim is limit of Xn must be equals to X. Okay, so let's start with let epsilon greater than 0 be given. Let epsilon greater than 0 be given. So when you use the property of the supremum, that then certainly x minus epsilon, if you differ x with epsilon, is no more an upper bound of the set. Okay, then x minus epsilon is not an upper bound of the set xn such that n belongs to natural number. Right? That's it, if and only if. Right? We have already seen this result as if and only if. Right? Now, any question? Okay. So then x minus epsilon is not an upper bound. So it's not an upper bound means what? This implies there certainly exists a member xk and it certainly depends on epsilon. Okay, such in S or in Xn such that n belongs to natural number, such that this xk epsilon is greater than x minus epsilon. Means x minus epsilon is less than xk epsilon. Now, since the sequence is monotonically increasing, so what it can tell you, this implies x to the power n is greater than x minus epsilon for all n greater than equals to k epsilon. Can I say this? Right, because xk epsilon is less than equals to, so you note that since the sequence is monotonically increasing, so therefore xk epsilon is less than equals to xn whenever n is greater than equals to k epsilon. You take any n bigger than that, it certainly holds. So now this implies x minus epsilon is less than xn, which is certainly less than x because x is supremum, and which is certainly less than x plus epsilon since epsilon is greater than 0 for all n greater than equals to k epsilon. So this implies, so you take xn x here, and then what it will say is minus epsilon less than xn minus x less than epsilon for all n greater than equals to k epsilon. And this certainly implies mod of xn minus x is less than epsilon for all n greater than equals to k. So this establishes our claim that xn is going to be convergent and converges to x. Okay, right. So when a sequence is have behavior monotone, correctly increasing, and if it is bounded, then it converges and converges to the supremum of the set. Okay, so how do you utilize this result is, so if I recall one example, so you had the sequence like the sequence x is equals to 1 by n, or not this sequence. Okay, we are going to use this. Okay, not a problem. Now note that xn, so note that x is decreasing and bounded. So x is decreasing and bounded. So therefore limit of x or limit of xn is nothing but the infimum of the set 1 by n such that n belongs to natural number, and which we have already shown that is equals to 0. So this is another way to prove that that limit of 1 by n is 0. So you need to only show that infimum of this set is 0. Similarly for 1 by n square, 1 by n square plus 1, or sin n by n, okay, and so on. Okay, right. So this is one of the example for monotonically convergent. Monotonically which is convergent if and only if it is bounded. Now let's take one example here, okay, which we are going to show. So let's take the sequence x is equals to xn such that xn is equals to 1 plus 1 by 2 plus 1 by 3 plus and so on plus 1 by n. This is also called harmonic series. Okay, now see this sequence is you can have, you know, that xn plus 1 is equals to what? Xn plus 1 by n plus 1. So which is certainly greater than xn. Similarly, greater than xn minus 1, greater than xn minus 2. So this is a increasing sequence. Okay, bounded below by 1, right? Yes. So bounded below by 1 because they are adding 1. So x1 is going to be 1. So it's bounded below by x1, that is equals to 1. But what about the upper bound? Whether it has an upper bound? So if you run a computer program here, Okay, so you go that you will see that for n equals to 50,000 or n equals to lakhs, suppose you take n equals to lakh and sum up. Okay, that will be some of the numbers. Okay, so some number you will get. So then what you will feel that this is going to be bounded, but this is not true. Okay, so when your n goes increase, then it is going to be unbounded, and however the speed of, you can say, the speed of being closer towards infinity is very slow, so it's very slowly moving towards infinity. Okay, that speed is very low, but it's going to be unbounded. So how would you show this? It's a very tricky proof. Okay, so what you will hear is, so let me look at the, so you can see x2 is equals to what? 1 by 2. Okay, now suppose x4 is going to be 1 plus 1 by 2 plus 1 by 3 plus 1 by 4. So what is going to be? This is greater than 1 plus 1 by 2. Now 1 by 3 is greater than 1 by 4. So 1 by 4 plus 1 by 4. So that is equals to 1 plus 1 by 2 plus 1 by 2. So that is 2 by 2. Okay. Now if you go for x8, now this is going to be 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5 plus 1 by 6 plus 1 by 7 plus 1 by 8. Sorry, plus 1 by 8, which is certainly greater than 1 plus 1 by 2 plus, so 1 by 4 plus 1 by 4. So 1 by 4 plus 1 by 4 plus, now each term is greater than 1 by 8. So 1 by 8 plus 1 by 8 plus 1 by 8 plus 1 by 8. So that is 4 by 8. So that is equals to 1 plus, that is equals to 1 plus 1 by 2. This is 1 by 2. This is also 1 by 2, 3 by 2. And so on. So you can show that x2 nth term is greater than 1 plus n by 2 by keeping this as like at a once. Here it is taking here 2 pairs for 1 by 3 plus 1 by 4. So you are moving with 2 to the power n term. Okay. So this is going to be greater than 1 plus n by 2, and you know this sequence is not bounded. Okay, so this does not converge, so this also does not converge. Okay, so this will remain, this will go towards infinity as n goes to infinity. Okay, right. So this is a harmonic series which does not converge. Okay, so how? So if you replace here alternate y plus y, alternative plus minus, okay, then you will able to see that this becomes convergent. Okay, that we will look at in the next session. So okay, fine. So we are closing here.